Okay, continuing on with this activity, 115, we're going to look at problems 8, 9, 10, and 11. So we have a pulley system where pulley A is moving at 1500 RPMs, has a diameter of 15 inches. All right, the belt will attach to pulley A. A will be the driver, and then the belt will attach to either B, C, or D, one of them at a time, but not all three. All of those are attached to a single output axle. So the idea is that the belt can be moved from B to C or C to D or vice versa around to manipulate the output speed and torque available at that output axle. So for number 8, our drawing might look something like this, okay, where we have a motor driving pulley A, and then on a single axle having 3 pulleys, B, C, and D. Or maybe it's B, C, and D. At this point, I wouldn't really know yet which one's bigger or smaller or what their sizes are. Okay, they've told me that A is going to be driven at an angular velocity of 1500 RPMs and that it has a diameter of 15 inches. Okay, so there you go. That is my, my lighting's a little off, I know. I don't know if I can somehow fix that. Oh, that makes it worse. If I hit autofocus, if that... Okay, I think I fixed my lighting issue, hopefully, for the most part. So let's go back and look at number 9. Number 8's done, that was my annotation. Number 9 says a speed of 1,750 RPMs is required when the drive belt is connected to pulley B. So I'm going to just jot that down in my notebook. We have an angular velocity at B of 1,750 RPMs. It says, what is the diameter of pulley B? Okay, so by having the driver's RPM and we have the desired output RPM, those two can be used. Remember, it is with angular velocities, the ratio with angular velocities is in over out to come up with the gear ratio. But that ratio of those things, since we're kind of comparing apples to apples, that should give me the gear ratio. And another way to get the gear ratio would be to compare the diameters of these pulleys. And with diameters, it's supposed to be out over in. So both of these ratios are supposed to be equal to the same gear ratio. So we'll just set them equal. So we will say the angular velocity of the driver, A, divided by the angular velocity of the output, which is going to be B in this case, is supposed to be equal to the diameter of the output pulley, which is the diameter B, and then the input, which is A. So now plugging in what we know we have 1,500 RPMs for A and a required 1750 for B. The diameter of B is unknown, and the diameter of A is 15. Alright, to solve this, we're really just trying to get this alone, and right now it's being divided by a 15. So if we simply multiply both sides of our equation by 15, we'll have isolated our variable, which is the diameter at B. And now it's just a matter of simplifying this expression. You also could have looked at this as a proportion, which would have been 15 times 1500 is equal to dB times the 1750. In which case you would have then turned around and divided by 1750. You'll note that this expression, it's the exact same math. We really want the product of 15 and 1500 and divided by 1750. So let's pull up a calculator right here on the screen where you can see it. And we'll just type that in. So 15 times our 1500, divide that by our 1750, and we get a approximate, well, how about I'll round this to the nearest hundredth, 12.86. and that's in inches because our 15 was in inches. So that's the required diameter for pulley B, which means it's going to be slightly smaller than the driver at A. All right, looking at number 10, it's very similar, very much the same question. They just have changed from pulley B to pulley C, and they've changed the RPMs to 2000. So they're saying that if we move the belt from B to C, we want to get an increase in RPMs, and we would like to get 2000 RPMs. So then the question is, what is the diameter needed to make that happen? Okay, so for number 10, it's going to be pretty much the exact same problem over here. Let's put it this way. So the diameter of A, not the diameter, sorry, the angular velocity of A over the angular velocity of C is going to be equal to the diameter of C over the diameter of A. The properties of A are going to stay consistent of 1500 and 15 inches. What's going to change is the angular velocity of the output. We're at a different pulley and we're wanting 2000. Okay, so again, you're going to multiply both sides by 15. And we're going to go figure out what is this diameter. If we multiply 15 and 1500, it's going to give us the same product again, 22,500, and we're going to divide that by 2000. And we're going to get 11.25. So that means that pulley C has to be smaller than pulley B. See, I might not have known in the beginning if I tried to guess which pulley is B, C, and D. Maybe I would have made the small one B, that C, and that D, but really, between those two, C's got to be smaller than B. And lastly, number 11, it's the same thing. Well, let's get back to the handout. What did they give you? I forget. 3250 is the required RPMs at D. So we're going to have the angular velocity at D, and that's going to be 3250. Alright, so we will multiply both sides by 15 again to get that required diameter. So our 22,500, that's our 15 times 1500, and that will get divided by 3250, and it's 6.92. I'm going to round there. I don't know if they told you to round to any certain place value. I didn't really pay attention to that. That'll be in inches. So based on that, I can come up here and I can say that D, if I want to label these, D is actually my smallest of the three, comparing them. C was the middle, and B was the largest. So we had a diameter of 12.86. That was for B. A diameter on C of 11.25, and a diameter on D of 6.92. There you go.